so here's problem number 9. And we're going to revolve this blue region around about the y, not the x-axis, the y-axis. And when I do so, I get a reflected image there, and all of my cross sections are circles. If I wanted to calculate the volume of that solid, what I would need to do is take the integral of all the cross-sectional areas and add them all up after I multiply them by a little bit of thickness. Now, in this case, my fingers for thickness are in this orientation, which means that my thickness is y's, which means my cross-sectional areas need to be functions of y. Now let's see. For some particular y on the axis of rotation, this point right here is going to be the point x comma, oh, I'm sorry. I don't want to write it that way. Since they wrote it this way for us, this would be tangent of 4 pi y, comma, y. Or the distance from here to here, which is measured horizontally, is going to be that value, tangent of 4 pi over 4 divided by y. If that's my radius, it seems to me that my area is going to be pi times that value squared. This is a description of the area. dy is a description of the thickness. Area times thickness is a little bit of volume. What is my lowest y value? 0. What is my highest y value? 1. All right. We've got the integral written. Now the question is, can we actually evaluate that integral on those limits of integration? I certainly hope so. Let's do a couple of cleanup things first. Let's pull that pi out. So I now have pi times the integral from 0 to 1 of tangent squared of pi over 4 times y dy. And I say to myself, do I know a function whose derivative is tangent squared? Sad trombone sound? No. Do-do-do-do? No, sad trombone. Wah, 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 wah. All right, so can we do this? Well, two opportunities here. Either we can use finite integral at this point and get a estimate to the value of this integral, or we can remember that tangent squared x plus 1 is equal to secant squared x. Yes. No? Yes. No. Which is it? Is that a true statement? Is that? Let me double check. Sine squared plus cosine squared equals 1. And if I divide everything by cosine squared, I get tangent squared plus 1 is equal to secant squared. Or that means that tangent squared x is equal to secant squared x minus 1. Or that I can rewrite this as pi times the integral from 0 to 1 of secant squared pi over 4 times y minus 1 dy. Can I do that integral? Do I know a function whose derivative is secant squared? Yeah. So pi times the antiderivative of secant squared is tangent pi over 4y on the inside and 4 over pi on the outside. Why? I'm doing the chain rule backwards. Or essentially I'm doing a u substitution in my head. I know that if I did the u substitution, that if u is 4 or pi over 4y, that after I did do the derivative step and divide, that the reciprocal would end up on the other side. So I did that all in my head. You may have to write it out explicitly until you can do that in your head as well, but it's going to end up being the same. What's the antiderivative of negative 1? How about negative y? And how about we evaluate this from 0 to 1? Now, if I evaluate this from 0 to 1, I'm going to get tangent of pi over 4. When I put 1 in here, I get tangent of pi over 4, which is 1. 1 times 4 over pi is 4 over pi. And then over here I get a minus 1. Minus, now let's do the same thing with 0. Tangent of 0 is 0. And minus 0, I get 0 minus 0 there. Or if I distribute the pi through here, I get 4 minus pi for my final answer, which I really hope is right. It is? Oh, of course it is. It's right here. Okay. So, what did we do again? Drew the reflection, drew a typical cross-section. We tried to find out what orientation our differential is going to be, and then we try to write a formula for cross-sectional area using that variable. And that's our summary for problem number 9. Let's shut off this recording.